Hi guys, welcome to today's lesson. We'll be taking a look at Newton's laws, grade 11 physics chapter. Let's get to it. This chapter has 4 subsections: introduction, force, Newton's laws, and finally forces between masses. First, let me introduce the chapter to you. This is the chapter where we will explore Newton's 3 laws of motion and his law of universal gravitation. Here are the key aspects that we'll go through in this chapter. First, we're going to take a look at different kinds of forces, and then look at free body diagrams and force diagram, and then go and look at Newton's 3 laws of motion. And finally, we'll look at Newton's law of universal gravitation. First, let's define a force. What is meant by the term force? Force is anything that can influence change in an object. Forces can either change the shape of an object, move an object, or prevent an object from moving, or finally redirect an already moving object. Let's classify forces. First, we have contact forces. That is a force that needs to be in contact with an object to cause a change. When you are pulling something or pushing something, let's say you're pushing a door or pulling it, that's a contact force. And next we have non-contact forces. That is obviously a force that can cause a change without being in contact with an object. A great example of this is gravitational force and magnetic force rather. And the unit that is used to measure force is called Newton and represented by capital letter N. There are different types of forces that you will need to familiarize yourself with before you need to deal with Newton's law. The first force is normal force. That is a force that is exerted by a surface on an object in contact with it. Next, we have frictional force. That is a force that opposes the motion of an object in contact with the surface. And within frictional force, we have 2 types of frictional forces. Static friction is the friction that an object that is stationary experiences. An object that is about to move possesses static friction. And next we have kinetic friction. That is a force possessed by an object that is in motion. Next we have tensional force. That is the magnitude of force that exists in ropes, chains, and strings, or anything that provides support. Now that we've theoretically discussed some forces, let's see them in action in a couple of exercises. Exercise number 1. It states, Tom's friends are trying to start Tom's stalled car. The coefficient of static friction between the car's tires and the road is 0.25. If the car experiences a normal force of 11,760 newtons, what minimum force do the friends need to apply to start moving the car? Let's take a look at solutions. First, I write down my static frictional force formula because I was told that the car is stationary and hence it possesses static friction as I've previously mentioned. And substituting in the values that I got from the question, I get like a mu that is equals to 0.25 or coefficient of friction, and a normal force that is 11,760, and I have a static frictional force of 290 newtons. Now, what force do the friends need to apply? At minimum, that force needs to be equals to the static friction in order for the force to be able to overcome the static friction. And hence, the force that the friends needs to apply minimum is the 2,940 newtons force. Let's move on. What are force diagrams? Force diagrams are sketches representing real-world problems you're dealing with objects represented by a small box, and arrows represent forces acting on the object. Here is a force diagram of a book resting on a table. The book is resting, it's not moving left or right, up or down, so it sits on the table. That means it experiences 2 forces. The first force is the gravitational force, and the next one is the normal force. That is the force that we previously defined as the force that is exerted by a surface on an object that is in contact with it, and hence a book resting on a table experiences 2 forces, gravitational force and normal force, as you can see in my diagram. Next, let's have an example of a book now that's being pulled in opposite directions. Now that book experiences 4 forces. As before, it has gravitational force and normal force, and the 2 other forces that are pulling it sideways, that is FL and FR. respectively for force left and force right. Again, free body diagrams are sketches representing real-world problems you're dealing with, but objects this time around are represented by a small dot instead of a box for force diagrams, and arrows represented the forces acting on the object. Now, for the previous two book scenarios, we have these new free body diagrams. For the first one, the book is just resting on the table. There is the small dot representing the book, normal force and force of gravity on the left, and on the right we have the force diagram of the book when it's being pulled left and right, and again it has FL and FR and normal force and gravitational force. Now, learning how to resolve forces into components is an important step in physics because forces won't always be applied linear to the motion or in the direction of the motion. Sometimes they will be applied at an angle, and when that happens, you need to resolve it into components. Now, here's an object that is on an inclined plane that is experiencing a gravitational force. Gravitational force, we know, is always straight down towards the center of the earth, and hence it's straight down. Now, if that object is sliding up and down that incline, that gravitational force, if I don't know the components, doesn't help me much in my calculations, and hence I need to break it into two components, that is Fg parallel, that is the force that is parallel to the surface, and Fg perpendicular, that is the force of gravity that is perpendicular to the surface. And the formulas are on the right. As you can see, the formula for Fg parallel is mg sin theta or Fg sin theta, and the formula for Fg perpendicular is mg cos theta or Fg cos theta. That is for an object that's on an inclined plane and experiencing gravitational force. Next is an object that's on a flat surface, but the force is being applied at an angle. You can see that the force is applied at an angle theta. Now, if the object is moving up or down or to the left or to the right, that applied force doesn't help me much in my calculations, and hence I need to break it into components. Those components will be Fv for force vertical and Fh for horizontal force. And the formula to calculate the vertical force is Fa sin theta, and the one to calculate the horizontal force is Fa cos of theta. Now let's move on to Newton's laws. First, we're going to look at Newton's first law of motion, which states that an object will remain at rest or straight line motion unless it is acted upon by a non-zero net force. Now, there are a couple of scenarios when we have all experienced this law, even though we didn't notice it at the time. First scenario, when you kick a ball, if Newton's law is incorrect, that ball should remain moving. It should never slow down. It should keep moving at the same speed that you kick it with up until it reaches the end of the world, if that's possible, or it reaches space. But now, because it is acted upon by air friction and gravitational force, that ball eventually slows down and falls to the ground. Next scenario is when brakes are suddenly applied on a moving car. You must have noticed that when you're in a moving car and brakes are suddenly applied, you keep moving at that force until the seatbelt pushes you backwards. And the third case is when you throw a stone. When you throw a stone, again, it should keep moving up until it reaches the end of the world or space. But because it is acted upon by non-zero net force, frictional force, force of gravity, it eventually slows down and falls to the ground. Now, there are not much calculations involved with Newton's first law. And now we're going to move straight into Newton's second law of motion, which states that if a net force acts on an object, the object will accelerate in the direction of the net force. And this acceleration is directly proportional to the net force and inversely proportional to the mass of the object. And the mathematical representation of the Newton's second law is F net is equals to ma, as you can see on my screen. Now let's take a look at some examples. The first example, it states that a 35 kilograms box rests on a rough horizontal surface. A horizontal force of magnitude of 70 Newton is applied on the box, causing it to accelerate. It experiences a frictional force of 14 newtons. First, draw a free body diagram showing all the forces acting on the box and then calculate its acceleration. First, here's my free body diagram. First, I know that the force of gravity will always be present and the normal force will be present because there's a surface that is in contact with the object. And after drawing those two forces, I know that the applied force should also be represented, and I've been told that this object experiences friction and hence frictional force should also be present, and hence there are a total of 4 forces in this particular question. Now let's move on to the next step, which is calculating the acceleration of the box. First, I write down my equation. F net is equals to mass multiplied by acceleration, and this object moves sideways to the left and to the right, and hence now I'm only going to concern myself with the horizontal forces, and the net horizontal forces are applied force minus friction is equals to ma. Now here you have to choose a direction as positive, and if one direction is positive, let's say right is positive, that means left must be negative. In this certain case, I've chosen right to be positive, and hence the frictional force is to the left, it was negative, and hence I have F minus Fr is equals to ma. Now substituting in everything I know, 70 minus 14 is equals to 35a. Solving for a, I get 56 is equals to 35a, and hence acceleration is equals to 56 divided by 35, and hence acceleration is 1.6 meters per second square. Now let's take a look at another example, a little bit more complex one. It states that a truck of mass 2,100 kilograms is towing a car of mass 1,000 kilograms. The truck's engine produces a force of 5,000 newtons. The connected vehicle moves with an acceleration of 13 meters per second squared. 1/3 of the friction is acting on the car and 2/3 of the friction acting on the truck. First, calculate the total frictional force present and then calculate the tension in the rope towing the car. Refer to the sketch below, and there is the sketch. First, let's see the solutions. First things first, I first draw my free body diagrams. As you can see, although the question did not ask me to draw the diagrams, I know that these diagrams are going to help me in my calculations, and hence I've drawn them for my benefit. And next, I am going to start with my calculations. As you can see, I've reduced my diagrams into horizontal forces because the objects move horizontally. Now for the car, I know that F net is equals to ma, and F net acting on the car is tension minus friction is equals to mass multiplied by acceleration. Again here, I've chosen right as positive, and hence the tension is to the right and the friction is to the left, and hence it's T minus Fr is equals to ma. Substituting in everything I know, the tension I don't know it, but I know that the friction on the car will be 1/3 of the total friction, and hence I have 1/3 Fr is equals to 1000, which is the mass of the car multiplied by 13, which is the acceleration. And now solving for tension, I have the following equation, which is T is equals to 13,000 plus 1/3 Fr, and I'm going to label that as my equation 1. And now I'm going to move on to the calculations for the truck. I know again that F net is equals to ma, and again, in this case, there's the force applied, which is to the right, hence it's positive, and then there's the tension. This time around, the tension is pulling to the left, and hence it's negative, and again, friction is to the left, hence it's negative, and they're all equals to ma. Now substituting in everything I know, Fa I was told it's 5,000 newtons, the T I don't know it, and the friction I was told it's 2/3 of the total friction, and hence it's negative 2/3 mr, and they are all equals to 2,100, which is the mass of the truck, multiplied by 13, which is the acceleration of the truck. And now solving for T and making T subject of the formula, I get T is equals to negative 22,300 minus 2/3 of Fr, and I'm going to label that as my equation 2. But I've noticed that in both the truck and the car, there's the tensional force. That tension is the same, and hence the tension on the car should equal the tension on the truck, and hence equation 1 that I've solved for the car before should equal the equation 2 that is for the truck, because both of them, they are representing tension. And doing that, I have 13,000 plus 1/3 of friction is equals to negative 22,300 minus 2/3 of the friction. And solving for FR, I have 1 over 3 FR plus 2 over 3 FR is equals to negative 22,300 minus 13,000, and 1 over 3 plus 2 over 3 will give me 1. Hence, I will have FR is equals to negative 35,300 newtons. Now, moving on to calculate the tensional force. I know that for equation 1, T is equals to 13,000 plus 1/3 of friction. Here, you don't necessarily have to choose equation 1. Either you choose equation 1 for the car or 2 for the truck, the tensional force that you will get will still be the same. I've just chosen equation 1 because that's what I wanted to do. But even if you choose equation 2, you should get the very same answer. And substituting in the friction that I got, now, as you can see that the friction that I've substituted there, it doesn't have a negative sign. Why? Because the negative sign only tells me the direction of the force. It doesn't tell me anything else about the magnitude. And hence here I'm only concerned with the magnitude and not the direction. And hence I've substituted in the 35,300 without the negative sign, because the negative sign only represents the direction. And hence I will have the tensional force of equals to 24,766,67 newtons. Now let's move on to Newton's third law of motion, which states that if object A exerts a force on object B, then object B exerts a force on object A of equal magnitude but in opposite direction. Now let's move on to forces between masses. This is where we find Newton's law of universal gravitation, which states that every point mass attracts every other point mass by a force acting along the line of intersecting both points. The force is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. Or mathematically, F is equals to G m1 m2 divided by distance squared. That G is a constant, m1 and m2 are 2-point masses, and the distance is the distance between the centers of the objects. And this one we will explain it further or discuss it further when we are dealing with some calculation. And hence that brings us to the end of the lesson. Thank you for watching. To support the channel and help more students access free lessons, please like the video and subscribe if you're new to the channel. For additional learning materials and updates, visit our website using the link in the description below. Keep studying hard and I'll see you in the next one. Cheers.